dear students, welcome back to General Science 101. We are looking at the physics portion of this course. What we did last time with you, we looked at the differences between heat and temperature. We said heat is the amount of energy which a body possesses, and heat, like any energy, flows from a higher level to a lower level. Temperature, on the other hand, is the degree of hotness. The both are interrelated because in order to find out how much energy or how much heat a body possesses, we have to know its temperature. We looked at the causes or effects of heat. If you apply heat to an object, what happens to it? Of course, it gets hotter, and as a consequence of getting it hotter, it expands. It is normal expansion for almost everybody. Solids, liquids, gases all expand on heating. There are certain materials which do not expand on heating, but more about that later. We then said that we use this expansion of solids, liquids, or gases into some practical devices. And the practical device which we discussed with you over the last 3 lessons was that we used the expansion of liquids and gases to formulate a temperature scale, or in other words, we used it in a thermometer. Now, a thermometer basically uses the fact that when you apply heat or increase the temperature, the object has to expand. And therefore, by looking at the expansion and assuming that the rate of expansion is constant, we have a scale which has got to have a fixed point. What exactly is a fixed point? A fixed point was a point on the temperature scale where it has to agree to a value given by definition. And by definition, we have certain fixed points. For example, the freezing point of water, the boiling point of water. The freezing point of water is given a fixed point of 0 degrees Celsius, 32 degrees Fahrenheit, or 273 Kelvin, depending upon which temperature scale you are looking at. Then we had the second fixed point, that is the boiling point of water, or we say it is the steam point because we measure the temperature of the steam. And it has to be at 100 degrees Celsius until the temperature rises beyond the boiling point, which normally if you have water which is boiling, unless all the water disappears, the temperature of the steam cannot rise above 100 degrees. Therefore, we have an area in which we can measure the temperature and remain confident that it is 100 degrees Celsius. Now, we have 100 degrees Celsius, we have a 0 degrees Celsius. We divide the intermediate portion of this expansion between 0 degrees. The object was this much, it expanded. So this is the amount of expansion we are looking at. Now, when we're looking at this expansion, we divide this into 100 equal parts, and thus we have our definition of 1 degree Celsius. We then looked at interconversion of scales. We said you have 3 different scales. We were looking at the Celsius scale, the Fahrenheit scale, and of course we looked at the absolute temperature scale, which has 0 degrees Kelvin as the basic starting point. And we looked how to convert one form of scale into another form of scale. We looked at the basic relationship, which was the temperature in scale 1 minus the temperature of the fixed point, which in this case was the freezing point of ice or the melting point of water, divided by the number of divisions in this scale. In the case of Celsius scale, the number of divisions is 100. Therefore, we divide by 100. In the case of Fahrenheit scale, the number of divisions between the freezing point of water and the steam point of water is 180. Therefore, we divide by 180, giving us a relationship, and we derive these relationships. Now, in looking at the expansions of solids, liquids, and gases, we also stated that there are certain materials which in certain temperatures have an anomalous expansion. What we meant by anomalous was that it does not follow the general rule that when you provide energy, the object expands. Water is one such case. In between temperatures of 0 degrees, that is the freezing point of water, and about 10 degrees Celsius, the water behaves anomalously. It expands rather than contracts. When temperature falls from 10 to 0, it contracts rather than expands when you go from 0 to 10 degrees. Therefore, water has got an anomalous behavior, and that is one of the reasons why water is not used in thermometers, because it will behave anomalously, and therefore we will not be able to with confidence be able to state what the temperature of that water was if the water was being used in the thermometer. We looked at the consequences of this anomalous behavior and said that this anomalous behavior has got positive effects for nature. Positive effects are because water expands when it is cooled. In other words, it rises, and therefore the top of the oceans or the lakes freeze, whereas the bottom part of the oceans and lakes still remains in a liquid at a temperature of around 4 degrees Celsius, and therefore the marine life or the aquatic life survives the severe winters, and therefore fish and other aquatic marine animals can survive in that water. Now, we also stated that when you look at solids, liquids, and gases, solids expands, liquids expand, and gases expands. However, gases expand normally more than liquids, and liquids expand more than solids. When we were looking at the gases, we said because when you have a solid has got a fixed shape, and therefore it's very easy to measure the expansion. However, when we move into liquids or gases, liquids or gases do not have a fixed shape. A liquid, of course, will depend upon the container we contain it. For example, this beaker has water. If the beaker was in a conical shape, like in a flask, then of course the shape of that water would be different, and expansion, of course, would be different. Therefore, whenever we are looking at expansion of fluids, we also have to take into account the expansion of the container in which this liquid is placed. In gases, of course, we have a different situation. In solids and liquids, the molecules are very closely packed together. So it is very difficult to compress either a solid or a liquid, and you require a very large amount of force for a very small compression. However, in the case of gases, this situation is different. Gases can be compressed because the molecules are very far apart. And in the case of gases, we were looking at equal volumes or equal masses, and therefore we had 3 different laws which govern the behavior of gases when you increase the temperature. And basically you have the Boyle's law, which states that the pressure and the volume are proportional to each other, and PV is constant, they're inversely proportional, So pressure and volume are inversely proportional in Boyle's law. In Charles' law, basically you have got that the pressure and the temperature are related in the pressure law, and the volume and the temperature are related in Charles' law. All 3 are combined in Avogadro's law, which also leads us to the general gas equation, which is what we discussed later. We also then looked at the fact that in order to measure the amount of energy available, we have to look at the material which we are heating. For example, some materials will gain energy at a faster rate, the other materials will gain energy at a slower rate. This difference in rate basically depends upon the specific heat capacity of the materials, and we formulated relationships on that. We then looked at also the modes of transmission of energy. We said there are 3 modes, that's conduction, convection, and radiation. We also looked at the process of hidden heat, like we call it, which is latent heat, that whenever a change of state takes place, in other words, ice is converted into water, you have some energy which goes into breaking the different bonds, and that is why the temperature remains constant, even though we are providing energy. That's the term latent or hidden heat. We looked at latent heat of fusion and latent heat of evaporation. We also stated that evaporation can take place at all temperatures. However, boiling can take place only at a particular temperature. So boiling is theoretically evaporation at a particular temperature, which is defined by the boiling point. Now, going further, let us see why when I place a cup of hot tea and a glass of cold water on my table, the tea becomes cold and the water becomes hot. Like we said, heat is transferred from a hotter body to a colder body. Teacup is hot. The surrounding is cooled. Therefore, heat is going to be lost by the teacup to the surroundings. In the case of the cold glass water or the cold drink which I have on the table, it is at a temperature lower than the surrounding. Therefore, it is going to gain energy from the surrounding. Surrounding is going to transfer heat because it is at a higher level. The water is at a lower level. So heat is going to be transferred and the temperature of the cold drink is going to rise. Another question, we said when we are looking at the different modes of conduction, convection, can we do forced convection? Can we increase the rate of convection? Now, convection basically is a process with which gases or liquids lose or circulate among themselves the amount of energy that they are possessing. Now, if I take this beaker and heat it, there will be a circular circulation set up in which the hot liquid will rise, the cold liquids will sink. Now, this is a process which is going to be a tedious, a very lengthy process. The question is, can we speed it up? Yes, the answer is very simple. The cooling effect of any liquid will depend upon three things. It depends upon the difference in temperature. If this is very hot, the surrounding is very cold, the rate of energy released is going to be larger. The second thing it depends upon is the surface area. If I place the same amount of liquid in a very large basin, then the surface area is large and we are going to get a larger amount of heat conducted out. The third is the rate at which the air is flowing over that surface. Now, if this is just simple air, it will take a very long time to cool. But if I blow on this air, then this becomes cooler faster. And we've had that experience that whenever we have something which is very hot, we blow on it so that the temperature should fall, and we can then, of course, consume it. So in case of forced convection, what we do is we increase the rate of energy exchange by blowing air or some liquid over the surface. The practical example of this is the car radiator. In a car radiator, you have air flowing through the radiator. There's a fan there which is forcing the air through it. And second, when the car is moving, of course, the driving force, the speed of the car causes a lot of air to pass through the radiator, thus cooling the car. Now, let me pose another question. What is the mode in which piece of iron, a very hot iron, I drop it into this liquid? What is the mode in which this piece of iron is going to lose heat? The two modes which are going to be used here, it is conduction. The piece of iron is in contact with the liquid. It's in contact with the water, and because it is in contact with the water, it loses energy through conduction. And of course, then the convection of water itself circulates that energy, and the hot water rises, the cold water sinks, and this becomes colder and colder. How do we increase the rate? We basically stir the water, and by stirring it, of course, we are forcing the convection. Similar is the case in a ventilated room. If you have a ventilator in a room, the ventilator, basically you just open the ventilator, hot air will go out and the cold air will come in from the doors or any other openings which are in the room. In case we want a forced convection, we are going to add an exhaust there, which is going to force the air outwards and thus causing a convection current. That is what we had covered in the last 3 or 4 lectures. Now, what we're going to do today and in the next segment of our course is we are going to be looking at another type of energy. We said that energy is transferred by 3 means. That is, it was transferred by convection, by conduction, and by radiation. And in radiation, we said that radiation is a process in which energy can be transferred in a vacuum. And the example we quoted was light energy from the sun reaches us, heat energy from the sun reaches us, and there is space between the earth and the sun. What we are going to be looking at is not how this energy is transferred, but we are going to be looking at the behavior of light in terms of geometric optics. We are going to see how light is transferred from point A to point B, or in other words, when we say light, we mean all electromagnetic radiation. So we are going to be interested more in the optical behavior of light rather than the energy properties of light. What we are going to be discussing today is the laws of reflection of light and the formation of images in plane mirrors, convex and concave mirror, and we are going to derive the mirror equation with you. We will also do some other things as time permits. Now, when I say the electromagnetic spectrum contains large number of radiations which are available. They all have one thing in common. The one thing in common they have is their speed. All electromagnetic radiation travels at the speed of light, whether they are radio waves, microwaves, infrared, visible light, or X-rays or gamma rays, as these are different radiations in different part of the electromagnetic spectrum. You can look at an electromagnetic spectrum in your textbooks. It is also available on the web. I have enclosed a slide for this purpose, even though this is just for guidance. What we are going to be looking at is visible light. Why visible? Because then we can demonstrate exactly what we intend to do. Now, before we continue on this, let us look at some basic definitions. What is light? What do we say is light? You can see me because of a light. Light basically is energy which produces a sensation in our eyes and hence allows us to see. Now, a visible light, when we say visible light, it consists of all colors which we can perceive. That can be red, violet, blue, indigo, green, yellow, orange, the 7 colors of the rainbow. Plus, if somebody can see more colors than that, welcome, they have got more sensitive eyes. When we say a ray of light is basically the direction in which a light moves. It's just a simple line. Let's say if I have a laser, which I'm shining, and if we can see it, we can see this is going to be a ray of light. Now, when you have got a large number of rays, we say it is a beam of light, or a collection of rays or a bundle of rays is known as a beam. What is a parallel beam? A parallel beam of light is basically light which continues along. If it is 10 centimeters at point A and it is 10 centimeters at point B during its propagation, then we say this beam is a parallel beam. In other words, all the rays are aligned to another. What is a converging beam? A converging beam is a beam which meets at a point. A ray of light which converges or meets at a point is known as a converging beam. A ray, on the other hand, which is coming out of a point and moving in all directions, is a diverging beam. So we have looked at a parallel beam, a converging beam, and a diverging beam. Now, a piece of glass, is it luminous? If I turn the lights off, this will also become dark. Therefore, I say this is a non-luminous object. Any object which does not emit light is a non-luminous object. The table, this beaker which is on the table, myself, these are all non-luminous objects because they do not emit light. Any object which emits light, of course, is a luminous object. It can be this laser pointer, which of course you can see can emit light. It gives off a certain color, and that allows us to see things. Now, transparent objects or opaque objects, when we look at an object, let's say a prism, this is a transparent object because light can pass through it. However, a black colored object, when light falls on this, it is not transmitted. You can just see that it is just stopped. It does not pass through, and therefore we say this is an opaque object. Glass, water, these are all transparent objects, and for that matter, even air is transparent as far as we are concerned and as far as its definition states. What is a translucent object? We said if an object allows light to pass through, it is transparent. If it does not allow light to pass through, it is opaque. Now, translucent objects are basically which allow light to partially pass through. Like a piece of paper, if I take a piece of paper or I take a piece of oily paper and shine a light on it, the light will be, I will be able to see light on the other side of the paper. However, that light will not be transferred further, and therefore we say that sheet of paper or oily sheet, thin paper, etc. are translucent objects. Another couple of definitions. We will define these definitions as we go on. What is a real image and what is a virtual image? Any image which we can project on a screen is a real image. So the image which you are seeing of me on your television screens is a real image because it is being projected on your screen. A virtual image cannot be projected on a screen. For example, if I take a mirror and I look into a mirror, I can see myself. But when I look into the side, what is behind the mirror? There is nothing. I cannot really feel exactly where my image would be, even though when I can see myself in that mirror. So that image which cannot be projected on a screen is known as a virtual image. It is image in a mirror. When you look at in a mirror, the image which you see, Now, the mirror which we are seeing is a plane mirror, because if you look at curved mirrors, then of course there are situations in which you will get a real image as well as a virtual image. Now, what is the theory of vision? How do we see things? You can see me. Why? Now, there is a couple of lamps in these studios which are shining light on me. This light is striking me, it is being reflected by my body, and this is falling into your eyes, and you can see it just like in the diagram which is on your slides. You can see there is a source. You can see light directly from the source, or you can see light which is being reflected from an object, and because it is being reflected from an object, we can see that object. So the theory of vision basically tells us we can only see things from which either they emit light or they reflect light. If there is an image which is not reflecting light and not emitting light, we will not be able to see it. And a black color object, of course, which totally absorbs the surrounding light, is one such example. What we're going to be talking about now is reflection of light. When we say reflection, we mean that light is coming, it is bouncing back into the same medium. It is not moving from one medium to another. So if the medium does not change and light bounces back, we say light has been reflected. Now, in order to do a definition or a mathematical representation of what is happening, let us look at a diagram, a slide which is on your screens, which tells you that we have a plane mirror on which a ray of light is falling and it is being reflected. So you have a polished surface on which a beam of light comes, it bounces back into the same atmosphere. The ray which is coming towards the mirror from the source is known as the incident ray, and the angle at which it strikes the object is known as the angle of incidence. The angle is measured is basically from the normal to the incident ray. This is the angle which you measure, and on your slides it is represented by the word I, the small I. The reflected ray which falls out of this mirror is known as, of course, the reflected ray, and again the angle between the normal and the reflected ray is the angle which we are looking at, and on your slides it is represented by the word R. Now, there are two types of reflections. A, these are normal reflections, which would be like in a mirror and on a plane surface. Light falls, light is reflected. I have given you on the slide two different types of reflections. If you have a reflection which is very regular from a plane surface, that is known as normal reflection. If the surface is not plane, not smooth, but rough, has edges, then light which comes can bounce off in different directions. Because it is bouncing off in different directions, therefore we say it is diffused or scattered light. Now, scattered light, the intensity of the light should fall, because not all of the light is coming into your eyes. It is being scattered different way. So we have two types of reflections. We have normal reflection and we have diffused or scattered reflection. We are going to be looking at normal reflection as we continue on, because the laws of reflection take into consideration that we are looking at normal reflection. However, these can be applied to diffuse reflection also, but in diffuse reflection, then we have to look at individual surfaces. And for example, I have in a hand, light falling on this portion might be reflected in this direction, but light falling on my other finger might be reflected in a different direction. So this would be diffuse reflection because of the shape of my fingers. However, at each individual point, the laws of reflection are valid and are retained. Now, what are these laws? Very simply, there are two laws which we are going to be looking at. A, the first law of the reflection of light says that the incident ray, the reflected ray, and the normal to the reflecting surface lie in the same plane. What exactly does this mean? It means that if I have a surface, this is the incident ray, the reflected ray, and the normal, they should all lie on the table. Technically, it means if this is a vertical mirror, a ray of light is parallel to the surface. After bouncing, it will remain parallel to the surface. It will not move in any other direction. That is what the first law simply states. The second law basically states that the angle of incidence equals to the angle of reflection. Now, in our diagram, we have said I is equal to R. If we look at geometry, we can have other angles which are also equal, but there is a method, there is a reason why I and R have been chosen, particularly because when we go into the second portion of our lesson, which is going to be the next lesson, and we are going to be looking at refraction, we will find that the two diagrams have to have similarities, and that is why I and R are chosen as they have been. And of course, we are going to apply the principle of reversibility of light. This is a simple principle. It simply says, if I can see you, you can see me. In other words, light is going to travel the same path going towards you as it is coming from you to me. Technically, if I shine a light on you and you shine a light on me, they should follow identical paths. This becomes very important when we design optical instruments, which sometimes we have to, by necessity, design in the reverse order, that this object, this object, this object, even though the light is coming from the opposite direction. The principle of reversibility can be amply proven. You can just lay it out, series of optical devices, pass a beam of light and try to reverse it. You will find that it is reversible, and in other words, light will follow the same path on the way out as it passes on the way back. Now, let us look at the slide, which is again repeated on your screens. It says you have a plane mirror, you have the incident ray, the reflected ray, and the normal, which are lying on the same plane. That is the same surface. The law of reflection says the incident angle is equal to the reflected angle. Now, you will sometimes have mirrors which are not plane. For example, on the slide, I have given you two diagrams. One is of a convex mirror. A convex mirror, the reflecting surface is on the outside, whereas in a concave mirror, the reflecting surface is on the inside. Now, in this case, even though the angle of incidence is equal to the angle of reflection, the reflection is going to behave differently, which we are going to find out as we go along. Now, because these behave, the light behaves in a particular specific geometric way, we can use the laws of geometry to solve our problems, that how light is behaving when it is reflected and where to find the images after it is being reflected, or in other words, when I look myself in the mirror, where exactly is my image, how far behind in the mirror is my image, etc., etc. How do we use these ray diagrams is basically illustrated on the slide, which you have right now, that we have our plane mirror, which is placed vertically. You have the object O on one side, from which a blue colored ray is coming out, and it is being reflected into your eye. So we are seeing that object which is being reflected. In other words, I'm seeing the reflection of a real object. Now, where exactly is this reflection? In order to find this reflection, what we do is we draw a perpendicular from the object to the plane mirror and continue producing it further, and the reflected ray is produced or extended behind the mirror. Where these two rays meet is where the image is located. This has been done by experiments, and therefore we can very easily repeat it. In other words, when we look at the slide, we find that the incident angle and the reflected angle, now I and R, of course, you have, when you look at the geometry of it, you will find that the two triangles, which is image plane mirror and the central point, and the object plane mirror and the center point, become two congruent triangles. You have two 90 degrees angle, two same angles, side is similar, so you have got angle side angle on the left hand side equal to the angle side angle on the right hand side, making the two triangles congruent. In other words, this imagery tells us the image is going to be as far behind the mirror as the object is going to be in front of it. Now, in case of curved mirrors, we have to do some other few definitions. We are going to define a few things. One, you have now on your slide a curved mirror. A curved mirror, basically, you have a sphere from which a portion is cut, giving you a curved space, which is now your curved mirror. There are different types of curved mirrors there, but for our purposes, we are going to be looking only at circular curved mirrors. P is the pole. It is the center of the mirror. Whenever you have a mirror, the exact geometric center of that mirror is going to be the pole. C is the center of curvature. It is the center of that sphere from which this mirror has been made. And the principal axis is the line which joins the pole to the center of curvature, and that is the principal axis. Now, how do we use this ray diagram? We have two other definitions to complete our situation. One is the principal focus. It is the point at which light meets after being reflected from a curved surface, either meets there or appears to meet, as we will discover as we go along. So you have a beam of light coming, striking the mirror. It is being reflected according to the laws of reflection, that the angle of incidence and the angle of reflection are equal. Because of the curve, the light is going to be bending at different angles, and it will meet at a point F, which is known as the principal focus. The distance between the pole and the principal focus is known as the focal length, and the radius of curvature, R, is of course the distance from the center of from C to P, or the radius of that sphere from which this is made. Now, in plane mirrors, basically the size of the object and the size of the image have to be the same, because the lights do not bend. However, in the case of curved mirrors, the size of the object and the size of the image can change depending upon where you place your object and where you receive your image and that is what we are going to be looking at in our next subsequent slides. Now, how do we go about doing these ray diagrams? Now, whenever we're looking at a curved mirror, for example, this is a representation of different mirrors. You have a plane mirror, which is of course a straight line. In any ray coming here will go on according to the law of reflection of plane mirrors. This is a curved mirror in which it is a concave mirror, which the inside surface is the reflecting surface. So you have a mirror which is concave, light coming in it will bend inwards, light coming in it will bend upwards. The third type of mirror, this is a bulging outwards, and therefore this is the representation of a convex mirror. In this case, light striking upwards will move up, light striking in this portion will move down according to the laws of reflection, which says angle of incidence should be equal to the angle of reflection. In order to do the ray diagrams, we have to see that a ray which is parallel to the principal axis, which is parallel beam, and it is going to meet at the focus. So after reflection, it should meet at the focus. So one point which we have, that a ray which is parallel to the principal axis after meeting the mirror should pass or appear to pass through the principal focus, how we will continue. And the second ray which passes through the focus has to become parallel to the principal axis. A ray which passes through the pole and is parallel to the principal axis bounces back. These are the two basic rules, and if we follow these, we can find out where the image is going to be formed, whether the image is going to be larger or smaller, as we are going to be looking at. Now, when we are looking at the geometric optics of these diagrams, for example, on your slide, I have shown you a detailed in which a concave mirror is producing an image. You have an object which is OA, which is being reflected. A ray which is parallel, that is AM, passes through the focus, that is passes through F. So MF is the ray which earlier was parallel, strikes, and now it is passing through the point F. The other ray, of course, from point A to P, because it is meeting the pole, and therefore it is going to be bouncing back according to the angle of incidence is equal to the angle of reflection. So what we find is that the ray which is AMF and APB, they coincide, cross each other at the point B, which gives us the point of the image. Now, when we are solving these equations, we say that the focal length of a concave mirror is positive, the objective distance is positive, the image distance is also positive. Why are they positive? Very simply, we are taking it along a number line, along the x-axis. So anything which is to the right of P is taken positive, anything which to the left of P is taken as negative. in this case, all the distances f, p, and q, f being the focal length, p the object distance, and q the image distance, are all to the right of the pole. Therefore, they are all positive. If a ray of parallel to the axis, it is going to be reflected and is going to pass through the principal focus. If it is directed at the pole, it is going to be reflected as the angle of incidence is equal to angle of reflection. In the case of a convex mirror, now the reflecting surface is outside. I have another slide for you on which I have represented how this is depicted. You have an object again on the right hand side. A ray strikes, which is parallel to the principal axis, is bent and passes or appears to pass through the focus, because in case of a convex mirror, the ray is going to go outwards. However, we produce the ray downwards and find it passing through the apparent focus. And similarly, the ray which is passing through the pole is not deflected, and therefore we find the point which is the place of the image, where exactly the image is going to be, and we can then identify whether it is going. Now, in this case, what we find is that Q is to the left of the pole, and therefore it has to be negative, and P is to the right of the pole, therefore it is positive. Focal length is again to the left of the pole position, and therefore it is again negative. So the focal length is considered negative, the image is considered negative, however the object distance is considered positive. These are just relationships which are mathematical in nature and which allow us to solve the mirror equation, which we are going to be deriving as we go along. Now, in order to derive the mirror equation, let us look at the first slide which I showed you, mirror equation for a concave mirror. In case of the concave mirror, you have two triangles, which is AOP and BIP. Now, these two triangles, like we said, angle APO and angle IPB are equal, because that is given by the laws of reflection. Angle of incidence and angle of reflection are equal. The one or the other sides, OAP, AOP, and BIP are, of course, 90 degrees, and therefore we have two 90 degrees angle here, so that you have two triangles which are similar. So whenever you have two triangles which are similar, the sides are in the same ratio. So side A divided by side A dash, side B divided by side B dash, and side C divided by side C dash have to be equal. In our case, this becomes OA divided by IB should be equal to OP divided by IP. Rearranging, we find that MP over IB is equal to PF over IF. And PF over IF gives us OP over IP. Now, replacing these numerical values by the actual measurements, we know that PF, the distance from the pole to the position F, is known as the focal length. We replace it by F, and IF, of course, is going to be Q minus F. And similarly, the OP over IP is going to be P over Q. Rearranging, we find F over Q minus P is equal to P over Q. QF is equal to P multiplied by Q minus F. And rearranging gives us the lens equation, which is 1 over P plus 1 over Q is equal to 1 over F. This is the mirror equation. 1 over P plus 1 over Q is equal to 1 over F. The same equation is going to be used in lenses also. However, we have to be careful there, because in the lenses, the object is on one side of the lens and the image is on the other side of the lens, and we have to be careful about the pluses and minuses in order to solve our questions. Now, let us look at a worked example. How do we apply this equation? Let us see an object which is placed on the axis of a concave spherical mirror at a distance of 20 centimeters from the mirror. If the focal length of the mirror is 15 centimeters, we have to calculate the position of the image. The data which we have is that the object distance P is equal to 20 centimeters or 0.2 meters. Q, the image distance, is something which we have to find out. F, which is the focal length, is, of course, 15 centimeters or 0.15 meters. Looking at our relationship, 1 over P plus 1 over F is equal to 1 over P plus 1 over Q is equal to 1 over F. and substituting the value, we find 1 divided by 0.2 plus 1 over q has to be equal to 1 divided by 0.15. Rearranging, we find 1 over q is equal to 0.20 minus 0.15 divided by 0.2 into 0.15, giving you 0.05 divided by 0.03, or in other words, q is 0.6 meters away from the mirror. In this case, because it was a concave mirror, P, Q, and F are all positive, and the answer automatically tells us that Q is a positive number and it is 60 centimeters away from our mirror. Let us look at another worked example. Now, in this case, you have a convex spherical mirror at a distance of 20 centimeters, just like former, and the focal length is again 15 centimeters. Now we have to calculate the point of the image. In this case, we are going to use the same relationship, 1 over P plus 1 over Q is equal to 1 over F. That does not change because that is the basic mirror equation. However, the signs are going to change because you are going to use a convex mirror. In a convex mirror, we have P is equal to 20 centimeters. Now, F, of course, is to the other side of the mirror. It is a convex. Therefore, the focal point has to be behind the mirror, and that basically changes the complexion. And therefore, we have F is equal to minus 15 centimeters, and Q is something which we have to find out. So 1 over P plus 1 over Q is equal to 1 over F. We have 1 divided by 0.02, sorry, 1 over 0.2 plus 1 over Q is equal to minus 1 over 0.15, or giving us a value of 1 over Q is equal to minus 1 over 0.15 minus 1 over 0.2. Rearranging, we find this is equal to minus 0.35 divided by minus 0.03, giving us the value of Q is equal to minus 0.86, or in other words, the image is 8.6 centimeters inside the mirror. So it is going to be a virtual image because it is inside the mirror, and therefore it cannot be projected on a screen. Now, like we said, that whenever you're using light, you either increase the size of the object or you decrease the size of the object. Therefore, if you are going to increase or decrease the size of object, we are defining something new, which is known as linear magnification. Linear magnification is nothing else but the ratio of the size of the image divided by the size of the object. If the size of the image is larger, you'll have a magnification which is greater than 1. If the size of the object is larger, you're going to have a magnification which is less than 1. So magnification of 1, of course, means that the image and the object are of the same size. So magnification is simply defined as the size of the image divided by the size of the object. Now, where do we use plane mirrors? Plane mirrors, of course, they are just not simply used to look at myself in the morning, comb my hair, or perhaps straighten my tie. They have other uses, other practical uses. One of the uses, of course, is a periscope. On your slides, I have shown you a simple diagram of periscope which uses two plane mirrors to bend light into a particular path. And this allows us, because light strikes the first mirror, it is reflected vertically downwards, it strikes the second mirror and is now visible. This is in a device which is normally used in submarines, so that when the submarine is underwater, or perhaps a person is standing behind an obstruction, wants to look over the obstruction without exposing himself to that hazard, whichever is there, and that is where this plane mirrors can be used. Another use of plane mirrors is, of course, at sharp bends of road. If you have a road which is bending very, very sharply, it is sometimes very difficult to estimate whether there's a vehicle approaching from the other direction. So normally you have a plane mirror which is placed at the intersection of the road, and therefore you can identify that whether there is something else approaching or not. Because of the inherent properties of plane mirrors, that they do not decrease the size of the object, therefore these plane mirrors have now been replaced with curved mirrors on the bend of the road, so that a person driving a car can differentiate between the image in a mirror and the object on the road, because in the mirror you are going to be seeing objects which are going to be smaller or larger than the thing. Now, where do you use spherical mirrors? Spherical mirrors basically are used in beams of light. You have a bulb which gives out a ray of light, giving out a parallel beam, because we know if anything is at the focal point, a beam coming out of the focal point after reflection is going to become a parallel beam. It is used by doctors in optical instruments and in astronomical telescopes. Now, let's again pose the question. We have discussed it. Now let's put it in specific terms. Why image distance and the focal length of a convex mirror is negative? Like I stated at that time, we are looking at the object distance and the image distance like in ordinary geometry or in algebra, where we say the 0 point is the pole point. Anything to the left of the pole is negative, anything to the right of the pole is positive. On your screen you are seeing two slides which show a convex mirror and a concave mirror, and you can see that in a concave mirror the focal length, image distance and the object distance are all to the right of the pole, and therefore they are all positive. In case of a convex mirror, the focal length and the image distance are to the left of the pole, and the object distance is to the right of the pole, and therefore two of them, that is the image distance and the focal length, are negative, whereas the other is positive. Now, how do you distinguish between a convex and a concave mirror? Very simply, a physical bulge. A concave bulges inwards, convex bulges outwards. About the reflecting surface. In case of a concave mirror, the reflecting surface is inwards. In case of a convex mirror, it is outwards. When a parallel beam falls on a concave mirror, it converges at a point. When a parallel beam falls in a convex mirror, it expands, or in other words, the focal point is behind the mirror. And of course, in a concave mirror, the image distance, the focal length and the object distance are all positive, and in a convex mirror the object distance is positive and the image distance is negative. And that basically what we have looked at. What we're going to be doing in the next lesson is we are going to be looking at another property of light. What happens when light moves from medium A to medium B? Reflections, we stated in the beginning, are only when you remain in one medium. In other words, reflection from air back into air, reflection from water back into water. Now we are going to be looking at, in the next lesson when we come, is what will happen if light moves from one medium to another medium. So what we have done today is basically defined for you the different terminologies which we are using in geometric optics. We are looking at the behavior of light. We said light travels in straight lines. It behaves as ordinary geometric objects, and we defined the angle of incidence. We defined the angle of reflection. We stated what is a normal. We looked at the laws of reflection of light. We said the laws of reflection of light are two. That is, the angle of incidence is equal to the angle of reflection, and second, the incident ray, the reflected ray, and the normal lie in the same plane. And we are going to continue with this in next time we meet. Thank you very much.